Hello and welcome to Toddcast number 50. So it's going really, really fast. But we're starting into the alcohol chapter, and this is going to be one of those chapters where we have lots and lots and lots of information to process. So we've covered a good amount of it, and so that's what we're going to do in the first couple Toddcasts. But this is the kind of the start of where the reactions we've learned will fan out very quickly into many different directions. Lots of things you can do with alcohols, lots of ways you can make alcohols, and they all are going to tie into some of the work that we did with alkynes, alkenes. We'll introduce oxidation reduction. We know they're involved in substitution, involved in elimination. So it's going to just quickly ramp up all the different options we'll have. So that said, I want to start with just what an alcohol is. So just to recall, an alcohol has an OH group connected to an sp3 carbon. The rest of the chain is kind of irrelevant. As long as you have the OH, I've drawn a 2-carbon terminal alcohol, but there's lots of others. But ethanol, fairly common solvent. Glycerol, used as a lubricant in one case. You're probably most familiar with this as a backbone in either fatty acid triglycerides, where you add 3 long-chain acids that turn into esters. So I'll just draw that real quick. Perhaps you've seen this in your bio travels. We get rid of the H from the alcohol. We get rid of an OH from the carboxylic acid. And then we have some long chain like this. Long chain like this. And long chain like this. So it's known as a fatty acid triglyceride. It's how we store our fats. But you may also know it from your travels in cell bio, where if you have something like this, have a phosphate group on the end, it's a phospholipid. So this is what makes up our phospholipid bilayer. So glycerol is the alcohol, the triol, because there's 3 of them, behind a lot of the biostructures we know. Isopropanol, known as rubbing alcohol. I guess it could be a solvent in OChem. We don't really use it as a solvent as such, just we have too many other good small alcohols like ethanol and butanol, but note that it is an antiseptic. Albuterol, asthma drug, so it's one, it vaporizes very quickly, so you put it in an inhaler. It can quickly act on the bronchi, just alcohol in 1, 2, 3 different positions. We're going to learn that, yeah, this is a primary alcohol, this is a secondary alcohol, but when it's on a benzene ring, it's known as a phenol. So this one has 3 OHs altogether, but we'll generally classify it as an alcohol and also phenol. So we'll get into that soon as well. Cholesterol, steroid has a steroid ring structure of 6-membered, 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 and 5-membered in this arrangement with an R group, some sort of alkyl group coming off here, a couple methyls at the quaternary carbons here, double bond, and then the OH making the alcohol. This tiny bit of polarity here, this tiny bit of hydrogen bonding cannot compensate for all the lipid nature here. So it's a highly lipid soluble molecule, incorporates in cell membrane to impact the fluidity of the cell membrane. Also serves as a synthetic precursor to pretty much every steroid hormone we have in our body. So all these have some common bio or lab utility. And so just want you to just be familiar with the functional group, but also have just some general information. Okay. Note the OH, 3 OHs, 1 OH. This one a little bit tricky, got an OH in one spot here, but again, the golden one, or orange as it may be in Pepperdine colors, the phenol, and then finally the last one on cholesterol. Okay, so that highlights alcohols. We'll also then reiterate just that phenols are a class of alcohols. They're a little more acidic. So if you remember the 5, 10, 10, 10, 15, 20, 25 rule, phenols are one of those 10s. So salicylic acid has a carboxylic acid group, also at the 2 position, has an OH, meaning this is a phenol. We have an OH on this ring. It's actually capable of forming a hydrogen bond between this group right here, or I guess this carbonyl, if it rotates over by 180, can interact with that H. intermolecular hydrogen bonding. Most importantly, we know this as aspirin. So it's a prostaglandin inhibitor. So it's anti-analgesic, or it's an analgesic, anti-inflammatory, antipyretic, pretty much anything, anticoagulant, anything that prostaglandins will do. This is responsible for suppressing prostaglandin formation. It inhibits the COX, one of the COX enzymes in the overall pathway of prostaglandins. Capsaicin, just one of those random molecules that you have in flavoring, so responsible for the hot chili taste. It's got the 1OH on the phenol, but you'll notice it's a long alkyl group. And this is one of those science experiments you probably didn't even realize. But if you eat really hot chili peppers and you get that burning sensation in your mouth and you drink water, how soluble is this compound in water? In reality, when you look at it, not very soluble at all. So trying to rinse your mouth with water after eating capsaicin is probably not going to do you much good. But if you ever heard that you're supposed to drink milk, that'll help. True, the lipids in milk, just a high enough amount that starts to dissolve it a little bit more and rinse it, I guess, out in your taste buds and down your gullet. Probably if you lick butter, not recommended, but that said, a lipid would dissolve this, and hopefully that would help. Don't recommend licking butter following eating hot, spicy food, but in theory, it could work. Epinephrine or adrenaline, neurotransmitter, one of those that's probably the most common. One of the things that we know, or I guess we know a lot about the pathway. Notice it has two phenols, known as a catechol. It all has an OH up here, so it's an alcohol as well. But I want to go one step further, that when you have two H's on a benzene ring in a 1-2 position or right next to each other, that's a catechol, and it also has an amine. So this is what's known as a catecholamine, which is a general class of neurotransmitters. And I took this from, the book, I use this as a reference, looked at a few other books, and I don't know what the obsession is with chemists who write textbooks, but they always seem to put some hallucinogenic or some illicit drug or something in there. So I have the option of tossing cocaine, THC, just all of these, but there you go. It's an alcohol. It's also a phenol specifically because the OH is on a benzene ring. So nothing sacred of this, not trying to say you should memorize all these structures, but just have a basic idea of functional groups as they appear in macromolecules. And the other moral to the story is a lot of our biomolecules are low-chem molecules that are a little more complex than just the simple cases I've been throwing in most examples, with functional groups that have a very significant role in this one position here or this one position here. They're responsible for binding, they're responsible for deprotonating and transferring something to an active site of an enzyme. They play different roles, but hopefully you're just familiar with the functional groups for this class. Okay, onward we march. So the phenolic OH, two phenolic OHs and one alcohol OH, and then a phenolic OH. Okay, we're color coordinated and off to the races. Alcohol properties, things you have to know. They form very strong H bonds, which allows for their miscibility or water solubility. One thing to make note of, the longer the hydrocarbon chain, the less soluble it becomes in water. So hopefully you remember that from one of the early labs that you did, where you tried putting methanol into water, it went just fine. Butanol, it didn't go that much, I mean, a tiny bit went in. And then one octanol, the long 8-carbon chain, didn't go at all into water. So there's that, as the chain increases, it becomes less and less soluble. We generally think of about 3 to 4 carbons as kind of that upper limit of how many we can put at least somewhat notable amount of carbon into water, complements of an OH or an NH2 or some hydrogen bonding functional group. So in this case, alcohol chapter, so we'll just say up to 4 carbon chain alcohols will have some water solubility, some notable measurable water solubility. Propane, just to point it out, no hydrogen bonding at all, very low boiling point, molecular weight of 48. I actually want to compare that to fluoroethane, and I picked this one because the molecular weights are roughly comparable. So I'm replacing a CH3, which weighs 15, with a fluorine that weighs 19. So it's the same ethyl group here with a methyl group here, but now with the fluorine. Notice that the boiling point goes up a tiny bit, weight gets heavier, but it really didn't change much, and it's polar. So we have this notion that polarity raises the boiling point, and it does, but really not that much. But as soon as I replace that fluorine with weight of 19 with an OH, a weight of 17, so again, they're all roughly comparable in molecular weight. Because they have the same molecular mass, we can say that aspect of the boiling point is comparable. But as soon as we add that OH and introduce hydrogen bonding, intermolecular forces increase to such a significant extent, boiling point goes from negative to suddenly highly positive, or if you will, goes up by over 100 degrees. So pretty substantial jump due to this H bonding. It's the same reason water has a really high boiling point, but methane, for instance, doesn't, or even methyl fluoride doesn't have a very high boiling point. But compared to water, which is 100, hydrogen bonding has a massive impact on intermolecular forces. You will learn in biochem, not only does it affect the boiling point, but it also affects the way a protein will fold, the way DNA will rotate into a base pairing situation. You've covered this in your bio classes, so you know how important it is, but it's the most important thing holding molecular structure, biological molecular structure together, and significant boiling point for what we're looking at. Methanol has a fairly high boiling point as well, and butanol we mentioned in lab, and octanol. So again, just want to go back to what we did in lab earlier. Methanol, highly water soluble, and butanol, semi-water soluble, and then octanol, the chain gets so long, its water solubility becomes negligible. So we have a hydrophilic end and the polar end. We have the hydrophobic end and the hydrophobic head. So notice I went from end to tail, and it's because it's long enough to call it a tail. But bioterms, the hydrophobic tail, the long alkyl chain, and the polar head. Most of the time, the hydrophilic or polar head is usually a carboxylate group, but in this case, going to use the alcohol as well. Okay, hopefully this seems reasonable and just brings back some familiarity. So lots of information. Just one of those things, you just got to hang on to a lot of this. So miscible in water, immiscible in water, and then somewhere in between, semi-miscible in water. Okay. The acidity of an alcohol. If you remember, it's 5, 10, 10, 10, 15 for acidity of an alcohol. So am I counting up? Their pKs are 15 range. I'm going to say they're actually a little bit higher. So 15.5 to 18 is a reasonable number. That's just straight alcohols. If you start putting fluorines on the backbone, for instance, you can actually lower it to lower than 15. But for straight alcohol, alkyl group with an OH, you should expect to be 15, 16, and in some extreme cases with steric hindrance or too much alkyl donation, it might start going up as high as 17 point something. Phenols, they're one of the 10-10-10s as mentioned. So phenol comes in right about 10. Ethanol, 15.8. T-butanol, when you suddenly have these R groups donating in, the steric hindrance, you'll notice the pK goes up. It's a little bit harder to take that H plus off. Cyclohexanol, around 18.2. So here's your 15 to 18 range. So when I say 15, it's a quick estimation, but most of them are actually slightly higher than 15. So that covers the physical properties, some of the information that I just want to get to lay the groundwork. Refamiliarize yourself with the functional groups. My hope is that nothing here was too terribly challenging. We're going to have another podcast that'll go over just some of the review of reactions you already know for these, elimination, substitution, just things that you've dealt with. And then we'll start getting into delving into much deeper information. So thank you for hanging out in the podcast, and I will see you at the next one. Bye.